Hello there. So in this next video, I'm going to be talking about probability density and normalization, specifically normalization of the wave function. And this is really the last video that I will do before actually getting into the Schrodinger's equation and actually solving the solutions to the Schrodinger equation for specific systems. But before I get into that, it's necessary to really know these two concepts, namely probability density and normalization, because they really are integral in trying to justify the meaning behind the wave function and what it even represents. So getting into this, there's this concept known as Max Born's postulate that tells us why the wave function for any given particle is meaningful. How we tie the real world to the actual wave function. Max Born's postulate tells us this. And what it tells us is the probability density, that is the likelihood of finding a particle at any given position, is proportional to the square of the wave function. So this, of course, just pertains to the spatial probability, or the probability of finding the particle at any given position in three-dimensional space. Later we're going to talk about how you can use the wave function to determine other properties, but insofar as finding a particle or measuring a particle at any given position, the wave function tells us the probability of finding it at any given position if you take the square of it. And so this is oftentimes the very first step in quantum mechanics in the discussion of the utility of the wave function. So one example of how a wave function can look like, and this is sort of bringing this a bit more concretely here, is drawn right here in this plot below. So here I have this wave function with respect to just one dimension, one position. And what I have here actually, and I kind of need to give a little bit of information about the system, is a particle that is located somewhere in space that is constrained between x equals 0 and x equals Lx. It's constrained on, some sort of potential. That is to say, you can think as an analogy of having, a ball in a box, right? A ball in a box. And, as you roll the ball in one direction or in the other direction, it's going to hit the wall and it's not going to be able to overcome, or it's not going to be able to, go through it, obviously. It's just going to collide with that wall. And there is an analogy here that we can take in the quantum mechanical world that is exactly like the situation of a ball being bound by these two walls in the side. And that is known as the particle in a box. Now, box is in quotes because it's not really a box in this case for quantum mechanics. It's actually some potential wall that it's hitting, and the way it's often plotted is as follows. You have a quantum mechanical particle, and actually there you go. So you have v of x in the x direction, and these walls, the potential of this goes off to infinity. That is to say, in order for a quantum mechanical particle to penetrate through the wall, it must have an energy that is infinity, which of course is not possible. And so if you recall the actual wave function, just so we know what this stands for, let me see. There you go. We have psi of x here is equal to E psi of x. And so what I have drawn here is actually, oh, and I made a mistake here, sorry about that. This is d squared dx squared plus. So this v of x here is this potential landscape here, where I'm defining this as x equals 0 and x equals Lx, right? And any particular state along this well is going to be constrained by the two walls, such that the wave function psi of x is going to equal 0 when x is equal to 0 and when x is equal to Lx. Right? So this is another way of stating that when this ball reaches the x equals 0 or the x equals Lx position, it's not going to penetrate it. It's kind of analogous to that. Later, we're going to see what happens when this is not infinity, when you have a finite potential. This statement doesn't exactly hold true. But for the case of the potential equaling infinity at 0 and Lx, this is indeed true. This is indeed the case. And this is one example of how a potential can look like for this infinite potential well problem, of how the, not the potential, I'm sorry, but how the wave function can look like. This is how the wave function can look like. Specifically, this is the second state, but we're going to get into that later. So now that we have an example of an actual wave function, and it takes a form of a sine, so this wave function here is proportional to, a sine function. It's some sine function. What does this really stand for? What does this really mean? And this is where Max Born's postulate comes into play. Essentially what this means is that if you take the modulus squared of this, function here, we end up with this guy down here. Okay, that's essentially this function up here squared, so you can clearly see that it is positive at every position. And Max Born's postulate is important because this gives us a probability density. That is to say, if we want to know what the likelihood is of finding a particle, let's say at this position, if we want to know the probability of finding a particle, let's say at within here, for example, somewhere in this range of positions, so we can call this x0 and x1, right? Then the probability of finding the particle at 0 or 1 comma 0, for example, is going to be equal to the area under this curve, ideally, right? It should be equal to, or we would like it to be equal to the area under that curve. However, obviously, the only way for this to be true is if we ensure that the area under the entire curve is equal to 1, right? That is to say, the probability of finding the particle anywhere must equal 1, because it has to be somewhere. Now, we know that it can't surpass x equals 0, nor can it surpass x equals Lx. And so, if we integrate over the entire curve, 0 through Lx, right? If we integrate over this entire curve, I'm just taking this function here and integrating all over, we should get you evaluate this to precisely 1, okay? And this is where the concept of normalization comes into play. What I did there is I normalized my function. Psi of x, okay? Now, we're going to get into precisely how to do this later, but just to be brief here, usually we have our function psi of x proportional to some constant a times sine of x. And it is this a that we solve for if we wish to normalize our wave function. However, if this holds true, then there is no need for normalization. But when we have this constant a, we need to normalize it by solving for it. But we're going to do that later. I just wanted to essentially introduce to you the concept behind normalization. And of course, just to finish this guy off, this probability off, the likelihood, presuming that this wave function is normalized, of finding the particle in this range is p10 x equals 0 to x equals 1 of psi of x squared dx. Okay, so I hope this brief introduction of probability density and normalization made sense, and we're going to go through much more concrete examples in the next couple of videos.